All right, this section is on the Cayley-Hamilton Theorem. Okay, so we saw that a square matrix can always be put into Jordan form. So that means we can always, for any A, again, A is complex n by n. So for any square matrix A, we can always write A is equal to Sj S inverse. Okay, so now if we look at taking multiples of K, so like for example, or of A, so for example, A squared, what would A squared look like? A squared is just A times A, so that's Sj S inverse. That's the first A, and then Sj S inverse. That's the second A. And notice here, S inverse is identity. So we're just going to get Sj squared S inverse. And we can do that K times. So there's the first A, there's the second, all the way up. And all of these inner SS inverses all cancel out. And so what we end up with is that A raised to the K is in fact S J raised to the K times S inverse. Now this is particularly simple. There is kind of general forms for these Jordan form raised to the K, but we're gonna basically focus on the attention where the algebraic multiplicity equals the geometric multiplicity for every eigenvalue. So if in that case J is equal to lambda, and in that case AK is again S lambda to the K, S inverse, and lambda to the K is just going to be all of the eigenvalues raised to the K. Okay, so we have this really nice expression. We can take A, raise it to the K, we get this form S lambda to the K S inverse. Yeah, so one might ask, what are the eigenvalues of A raised to the K? So in other words, I can write this form as A raised to the K S is equal to S lambda to the K. So what are the eigenvalues and eigenvectors of A raised to the K? Well, notice they have the same eigenvectors, and the eigenvalues are just the original eigenvalues of A raised to the K. So this is a really nice, nice form. Okay, now for square matrices, we can define analytic functions of matrices. So, for example, we have a number of analytic functions that can be expanded. Analytic meaning it has infinite number of derivatives. And these functions can be written in terms of their Taylor series because we can differentiate, infinite number of times. So e to the x is going to be 1 plus x squared over 2 factorial, x cubed over 3 factorial. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. And sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So these are functions of a scalar x. Well, we can define corresponding matrix functions in terms of their Taylor series expansion. So essentially, instead of x here, we're going to put a matrix. So E raised to the matrix A is going to be, instead of 1, we're going to have identity. Instead of x, we have the matrix A. Instead of x squared over 2 factorial, we're going to have the matrix A squared over 2 factorial, etc. And the same thing for, we can do cosine of a matrix. It's going to be in terms of its Taylor series expansion, and sine in terms of its Taylor series expansion. All right, so computing infinite series of matrices is a pain. So for example, and we saw in a previous discussion that in fact e to the at gives us solutions to the differential equation. In other words, we saw if we have this differential equation, x dot equals ax with initial condition x naught, that the solution was x of t is equal to e to the at x naught. So computing this guy is, is important. We can solve linear constant coefficient ordinary differential equations. Any nth order linear constant coefficient differential equation can be written as in this state space form. So basically, any linear constant coefficient differential equation, the solution is given by this e to the at. Okay, so how do we go about computing that? All right, so computing infinite series is a pain, and that's where the Cayley-Hamilton theorem comes in. So I'll explain how we use the Cayley-Hamilton theorem to satisfy or to solve these equations, or to find an infinite series in a very slick way. But first we need to state what the Cayley-Hamilton theorem is and prove it. Okay, so we're going to prove it just in the case where A is diagonalizable, or in other words, where the algebraic multiplicity equals the geometric multiplicity. But it turns out, for every eigenvalue, but it turns out that it's true for general matrices. Okay, so here's the Cayley-Hamilton theorem. It says that every matrix satisfies its own characteristic polynomial. Okay, now remember, we have, the characteristic polynomial associated with A, lambda, is equal to the determinant of lambda I minus A. And remember, this can be written in terms of a polynomial. Lambda raised to the n plus, alpha n minus 1, lambda to the n minus 1 plus alpha 1 lambda plus alpha 0. Okay, so if we write the characteristic polynomial in this way, what the Cayley-Hamilton theorem says is that if I take lambda A, and instead of plugging in lambda, I plug in the matrix A, then I get A raised to the n plus alpha n minus 1 A raised to the n minus 1 plus alpha 1 A plus alpha 0 I, that this thing is going to be equal to 0. Okay, so in other words, every matrix satisfies its own characteristic polynomial. In other words, I plug it into the characteristic polynomial, set it equal to 0, and A will satisfy. In other words, every A satisfies this as long as these coefficients, alphas, come from the determinant of lambda I minus A, like that. All right, so it's an interesting thing. It turns out to have lots of applications, but we'll talk about a specific application. Okay, so the proof, it turns out that this holds for all A, and you do it using the Jordan form, but we're only going to prove it in the case where the geometric multiplicity is equal to algebraic multiplicity for each lambda I. In this case, it's quite easy to prove, and so I'm going to just leave it at that, but just know that it holds in general. Okay, so if the algebraic multiplicity equals geometric multiplicity equals algebraic multiplicity for each lambda I, then we can write A in terms of we can diagonalize. So A is going to be S lambda S inverse, where lambda are all the eigenvalues, along the diagonal. S are the eigenvectors lined up in the columns of the matrix. Note, okay, so now we also know that for each eigenvalue, lambda, each eigenvalue satisfies the characteristic polynomial. In other words, we already know that so you take chi sub A lambda I, when the determinant, the eigenvalues satisfy this equation, right? The determinant of lambda I minus A equal to 0. So that's exactly what it means to be an eigenvalue, to satisfy this characteristic polynomial. So when this is true, so lambda, in other words, satisfies the its own characteristic polynomial. That's what it means to be an eigenvalue. Okay, so let lambda a, or chi sub a of lambda be this polynomial. So here I'm using the coefficients a, n minus 1, a1 to a0. Okay, so now let's look at the matrix version. So when we plug the matrix in, we'll get a to the n plus little a n minus 1 matrix to the n minus 1 all the way down. And now we know that a raised to the n is in fact s lambda raised to the n s inverse. And a to the n minus 1 is s lambda n minus 1 s inverse, all the way down to a, which is s lambda s inverse, plus a0i, and identity, we can write identity as s inverse, right? That's just equal to identity. So now I'm going to take this equation. Notice there's an s on the left of each of these terms and an s inverse on the right of each of these terms. So I factor out the s on the left and I factor out the s inverse on the right, and what's left? Alpha, or lambda to the n, a n minus 1 lambda to the n minus 1, all the way down to a1 times lambda plus a0 times identity. Okay, so this thing. Now, note that when I take lambda to the n, that's just going to be each of the elements of, lambda 1 to the n. It's going to be diagonal, lambda 1 to the n, etc. And so this thing is diagonal, this guy's diagonal, that guy's diagonal, that guy's diagonal. So I add up a bunch of diagonal matrices, and each of these things, this matrix is going to be diagonal. And what is each of the diagonal elements? Well, the first element along the diagonal is going to be, or I guess maybe the ith element along the diagonal, it's going to be lambda I to the n plus a n minus 1 lambda I to the n minus 1, all the way down to a1 lambda I and a0 times 1. So it's this. And what, it's this guy. And what is that? That is the characteristic, that's just, this thing is just determinant of lambda I minus a, right? That's our characteristic polynomial. And it has to be equal to 0. All right, so this diagonal matrix, in fact, is equal to 0 down here. Okay, so we go back up here. This whole thing then has to equal 0. So the characteristic polynomial, chi sub a has to equal 0. All right, so we've proved the Cayley-Hamilton theorem, at least in the case when the algebraic multiplicity equals the geometric multiplicity. All right, now, how do we use this to help us with these infinite series? Okay, so this is, if we go back and remember how to do polynomial division. So, for example, let's think of remember if I have x squared plus 2x plus 1 divided by x minus 1. Remember how we do this? You would multiply an x up here, so that gives us x squared minus x, and then we subtract, and we get a 3x plus 1, and so then we would do a 3 here, and that gives us a 3x minus 3, and we subtract, and we get a 4 here. So this would tell us that x squared plus 2x plus 1 divided by x minus 1, it's going to be equal to x plus 3 plus the remainder, 4 over x minus 1. So So when I have I have some polynomial divided by another polynomial, f divided by q, I'm going to get some ax plus the remainder divided by q. Okay, so this is polynomial division. Back to what we did, I don't know, when was this, 4th or 5th grade. All right, so now you multiply through by q of x, and you get f of x is going to be a of x times q of x, and then the q cancels out, and you have an r of x. And let's just remember the degrees of these polynomials. So if f of x is degree n, and let's say q of x is degree m. So this is degree 2, that's degree 1. When we divide, we're going to get something that is, this degree minus that degree. So that's going to be a. It'll have degree n minus m. And then, the remainder back here has to be, this degree has to be less than q, the degree of m, or we could still keep on dividing. So the 4, this has to be less than that degree. So this would be degree 1, this would be degree 0. So r of x has to be degree less than m. So if f has degree n, q has degree m, that means this a is degree n minus m, and the remainder has to be degree less than m, the thing we divide by. Okay, so let's look at infinite series. Okay, so we have an infinite series, e to the x. It has degree infinity. And let's divide by the characteristic polynomial, okay, that has degree n. So if we divide by that, then we'll get some ax, and because this is n, I guess this is our m up here. This would be n minus m. Yeah, maybe I'll just make just to make this. I'll change that in the next version. Okay, so this because e to the x has degree infinity, we divide by something with finite degree. Ax has degree infinity, but the remainder has degree less than this guy. It's going to be less than the degree of the characteristic polynomial. And since a satisfies its own characteristic polynomial, when I plug in e to the a here, I'm going to get something times 0. So it turns out that e to the a has to equal to the remainder when I do this division. And the most important thing is it has degree less than n, where n is the size of the matrix A. Okay, so this thing Rn is equal to, there shouldn't be any dots there, it's equal to some polynomial of degree less than n. So in other words, there's some bn minus 1 down to b1, b0, where the e to the a is equal to this guy. Now, we could make the same argument about the eigenvalues. Like if I go back up to this equation and I plug in e to an eigenvalue, lambda I of a, it's going to be some polynomial, and now I'm going to have chi sub a with the eigenvalue, and that guy's equal to 0 at the eigenvalues. So this whole thing is 0. So if I plug in just the eigenvalues, then e to lambda I is going to be r lambda I. So we can find the coefficients. These, how do we find these coefficients? We don't know what those are, and we don't want to do this division, of an infinite dimensional polynomial. But it turns out the eigenvalues satisfy this equation as well. So we can plug in lambda I. We can plug in lambda i's here. I equals 1 to n. And this gives us n equations and n unknowns. So we have n equations and there's n unknowns from which we can solve this expression. So, for example, if I want to find e to the a, where a is equal to this guy, Okay, so the determinant, we need to find the eigenvalues and eigenvectors, or we need to find the eigenvalues first. We don't need to find eigenvectors. So the determinant of lambda I minus a, this is the characteristic polynomial. So this is going to be chi sub a of lambda is going to be the lambda I minus a, and when we plug that in, we get lambda squared plus 2 lambda plus 2. And so the eigenvalues, the first and second eigenvalues are minus 1 plus or minus j. All right, now we know that e to the a is going to be some b1 times a plus b0 times identity. This is that goes back to our equation saying that it has to be the remainder. In other words, e to the a has to be a polynomial of degree less than 2. So, we have this is of degree 1. There's no squared here. So we have to have e to the a has to be a polynomial of degree 1. So it's going to be some b1 times a, and here's when I multiply b1 times a, there's b1 times a, plus a b0 times identity, there's b0 times identity. I add them together and it has to equal that. So e to the a has to equal this guy. And b0 and b1, how do we find those? Well, b0 and b1 have to satisfy when I plug in the first eigenvalue, minus 1 plus j. When I do e to the first eigenvalue, that has to be b1 times the first eigenvalue plus b0. When I plug in the second eigenvalue, it has to be b1 times the second eigenvalue plus b0. So I can form a matrix here. I can write all of that, and that's in terms of b0, b1, and so we would have 1 minus 1 plus j and 1 minus 1 minus j. So I need to invert that matrix multiplied by e to the minus 1 plus j, e to the minus 1 minus j. And when I multiply these together, I get these numbers. And now if I take these numbers and plug it back in here, I get this matrix. So the exponential raised to this matrix is going to be another matrix, and it's exactly that guy, which is, we would get through the infinite sum, but the Cayley-Hamilton theorem gives us a slick way to solve for e to the a. Should note that you could also find, for example, maybe as a exercise not to turn in, what is cosine of a or sine of a? How would you find those? Okay, so that might give you a little bit of practice.